Okay, welcome back. I'm going to finish up the week 5 part 1 material about random Python things that we missed, and then continue with the week 5 part 2 material, which is more things that we missed. I think we talked about the inline if-else in live lecture, but let me start here. So you can have an expression that is an inline if-else comparison that produces a value. And the value of the expression will be the first sub-expression of the inline if-else if the test expression evaluates to true. Otherwise, if the test expression evaluates to false, the value of the overall inline if-else is the final expression, or the expression from the false value. So here, for example, I'm asking the user to type in their age. I'm going to assume that what they type can be converted from a stir to a float successfully. When I hit the enter key and that input function runs, it displays the prompt, your age. And if I type in 42.1, of course, that's the string 42.1. And that can be successfully converted to a float. And now I'm going to try to detect whether this age represents an adult or a child. So the status of this person is adult. That's going to be the overall value of this inline if-else expression if the age is greater than or equal to 18, which in this case it is. All right, so because the age is greater than or equal to 18, the result of this is the string adult. But if the age that I had typed in was less than 18, then the value would be child. You can nest or extend inline if-else statements across multiple lines by using parentheses. Here I'm using parentheses around the else part of this nested inline if-else expression. Once again, we ask the user their age. The user typed in a 9 in this case, and that can be successfully converted to a float. And then we have this giant 4-part inline if-else. If the age is less than or equal to 1, which it's not, but if the age were less than or equal to 1, we would get baby as the result. Otherwise, we're going to get this entire chain of inline if-elses contained in this outermost pair of parentheses. So we test whether the age is less than or equal to 3. If that were the case, we would get toddler, but it's not the case. So we go to the next nested inline if-else in the else part here. If age is less than 13, well, in this case, this test expression is true, so we return the result, child. And once we have identified the result, that's it. We don't continue evaluating more of the further inline if-elses. All right. Next up is a trivial thing called the pass statement. Pass is included just for syntactical consistency. It is a statement that does nothing, but it does it in a syntactically appropriate way, okay? And often people will throw passes into their code sort of as a placeholder to mean, well, I know I have to have something here, but I will figure out later what the details are. Here I've got an example code file, pass_ex.py. In here I'm defining a function called foo, and I'm creating a class called x. I know that my class called x is going to need a dunder init function, and it's going to need a dunder repr function. But at this point, I'm just kind of sketching out the outlines of the functions and classes in this file. So I've used pass in here in 3 places to indicate, all right, I know I need these functions, but I will fill in the details after I have completed laying out the outline for these for the contents of this module. The del statement eliminates a reference to an object. We have previously created a data frame having various columns, and if we want to delete an entire column from a data frame, we use the del statement with the data frame and then subscripts in the particular column we want to get rid of. This also works, del also works with ordinary variable names. So for example, if I say s gets hello, now the variable name s is referring to the str hello. When I say del s, the variable name s no longer exists, and the string hello, because it no longer has any variable referring to it, the storage space for the string hello can be reclaimed and used for some other purpose. All right, so s no longer exists in this case. You can also eliminate particular items or particular slices from within mutable sequences. Here I'm going to create a list called m, which is just 10 values, 0 through 9. All right, so there's m. M sub 4, of course, is the sub 4 item, 0, 1, 2, 3, so not very clever. The value of m sub 4 is the value 4 in this case because of the range. I can delete that particular item out of m, and what I have left is the remaining 9 items. I can also delete an entire slice out of m. 2:5 here means from item sub 2, whoops, come here now. All right. From item sub 2 up to, but not including item sub 5. All right, so here's item 2, sub 3, sub 4. 6 would be the item sub 5. And so this del command, this del statement, is going to eliminate the 2, 3, 5 from the middle of this list m. Okay, so that's a handy thing to know. We can also use del to get rid of items out of a dictionary if we specify a key. This is very similar to deleting things from a data frame, for that matter. So let me just hastily create a very small dictionary. So we're going to have the key A associated with the value 123, and the key B associated with the value 41. All right, there's D. Here's D sub A. And if I say delete D sub A, then that key and its associated value are removed or eliminated or deleted from D. Now, del won't work with a tuple because a tuple is not mutable. So if I say T gets 5, 4, 3, 2, 1, let's say. All right, then I can ask for an item out of T. So let me ask for the sub 4 item. That's the 1 at the end. But I can't delete that item. All right. A tuple does not support item deletion. Now, you can, at the bottom of a loop, whether it's a for loop or a while loop, place an else clause. And I will confess to you that I find this objectionable. It bothers my aesthetics that we can have an else that doesn't have an if prior to it. But the idea is that what you put in an else following a loop is code that you want to have executed when that loop is finished. Now, there's one exception here, which is that if you have a break inside of your loop, then that will completely break out of the entire loop, including the else at the bottom of the loop. Let me just show you an example here. So I'm going to say I gets 10, and now I'm going to use a loop to do a countdown. While I is greater than or equal to 0, print I, and I want all these countdown values on the same line, so I'm going to say end is a space, and now I need to decrement my loop counter. So I minus gets 1. Now, when this whole loop is done, I want to display lift off or go or blast off or whatever. So I'll just say star star go star star. Okay, so the loop is going to run to its conclusion. When I reaches the value -1, the loop will stop. And at that point, the else will be triggered. And the else will, the body of the else, which is this print go, will be executed. There we go. So here's what the loop displayed. And when the loop was completely finished, we got space, space, star, star, go displayed within the else. There are a couple of standard top-level functions, sorted and reversed, that work on any iterable. What the sorted function does is to return a list of the sorted values of some iterable. This is very handy for any kind of iterable that can't be directly sorted. Now, we know that if I have a list of values, m gets whatever, 4, 1, 9, -3, 1, 2, 10, 3. Cool, I did that without making silly mistakes. We can, let me make a copy of that. M copy is m.copy. We know that a list is directly sortable. I can say m.sort, and by default, I get those values in ascending, or very technically non-descending order. But a lot of other, in fact, most other kinds of collections can't be directly sorted. We can't sort a set. We can't sort a tuple or a dictionary or what have you. But we can use sorted to get a list of values. So here's m. If I ask for, let me get m copy here. Let me get m as a copy. Let me restore m to what it was. So m is now its original sequence. Sorted m returns an iterable, returns a list of the values of m in sorted order. But that doesn't change m directly. I just noticed that there is actually a typo on my slide 26 here. These values, -3, 1, 1, 2, 3, etc., those should be contained within square brackets because the sorted function does return a list. Now, in addition to specifying the iterator that you want sorted to operate on, there are two keyword parameters that you can specify as well. The first one is key, which allows you to specify an alternate function to use to establish the key for sorting. The second one is reverse. The default value for reverse is false, but if we want the values to be sorted in reverse order, we can say reverse equals true. Let's have a look at that. Here's M, 419, etc. And as we've seen, if I say sorted M, that gives me back a non-descending sort of M without changing M. If I say sorted sorted M reverse equals true, then I'm going to get non-descending then I'm going to get non-ascending, which is approximately descending order, right? 10, 9, 4 down to -3. Once again, this doesn't directly change M. Here is an example of specifying an alternate key to use for determining the ordering of the values. All right, so I'm saying sorted M, but as my key, I'm going to use a lambda. Remember that lambda is just an unnamed function. I could have defined a separate function and called that function instead. But let me say that lambda of x is the absolute value of x. ABS is a built-in function that gives you back the absolute value of its argument. So what am I doing here? Well, I'm sorting the items within M in ascending order, that is in non-descending order, according to the absolute values. So I get 112, whoops, come here, come back. So I get 112, 3 minus 3, 3, 4, 9, 10. So the minus 3 was sorted according to its absolute value. Now, I do want to mention, in the result here, minus 3 is not coming out ahead of 3 because minus 3 is less than 3. Minus 3 is coming out ahead of 3 because minus 3 occurs earlier in M than 3 does. We talked before about the idea of a stable sort. So after you take the absolute value of minus 3 and the absolute value of 3, those two values compare identically, but this minus 3 comes out ahead of the 3 simply because minus 3 is earlier in M than 3. And likewise, although you can't tell, this first 1 becomes the first 1 in the sorted result, and this second 1 becomes the second 1 in the sorted result. Here's a tuple, T. Let me create this. 5, 1, minus 4, 2, 3, 12, minus 7. And of course, we know that tuples don't support sorting. But I can ask for a sorted copy of T, and I'm using the same lambda so that these are actually being sorted in order by absolute value, and I'm saying reverse equals true so that I get descending order instead of ascending order. When I sort anything using sorted, what I get back is a list. Okay, so when I say sorted on any iterable, what I get back is a list. But I could put that back into T, or technically change the variable T to refer to a different thing by constructing, come here, sorry, by using my tuple conversion function on this sorted list. All right, and now I have T. Still, T is a tuple. It's technically actually a brand new tuple, and it contains the values of the original tuple T in descending magnitude order. Reversed does not return a list. It returns a general iterable on the values in some argument iterable in reverse order. So if I have M still containing its original stuff, and I ask for reversed M, this is not going to look too useful. I just get told, hey, cool, this is a list reverse iterator object. Well, I have to use that reversed iterator in some kind of loop or some kind of conversion function in order for the reversing to do anything. Let me create M reversed as a list constructed from the reversed M. Okay, so we have exactly the same values in MR as we had in M, but they're in the reverse order. Or I could, of course, say for val in reversed M. Whoops, that didn't work. For val in reversed M, print val and equals space. And there we are. Okay, so we got the values from M, but displayed in reversed order by that loop on print. Now, the cool thing, or a cool thing about sort, is that it will work on sets and dictionaries, since sets and dictionaries are iterable. So, although you can't sort a set, you can extract a copy of the contents of the set and sort that. And that's basically what we're doing here. So I'm going to create a set containing 9, 1, minus 2, 7, 1, minus 9, 3, 8, minus 2. And I have some duplicates in here, intentionally. I've got 9 appearing, just once, I guess. 1 appearing twice, minus 2 appearing twice. So S itself only contains 7 values. If I ask for sorted copy of S, I get back a list as usual from sorted, and these things are in non-descending order. Similarly, I guess I'm not going to type this one in. It's just a little long. I can create a dictionary, and when I sort the dictionary, when you give just a dictionary name as an iterable, that is equivalent to asking for the keys of the dictionary. So what you get back is a list containing the keys in ascending order. You can also sort the items. Remember that the items extracted from a dictionary are tuples. And when you sort the tuples, they are first sorted on the sub-zero items within the tuples. And then if you had duplicates, which in the case of a dictionary, that can't happen. You can't have duplicate keys. But if you did, in some other context, have duplicate keys, then the sorting would do subsorting on the values. Okay? So, I guess I'm going to be stuck creating this dictionary. Let me turn off my highlighting. There. Now I can actually copy and paste. So, I'm going to say D gets, and then copy over this dictionary and hope there are not any strange, mysterious characters in there. Yay, it worked. Okay, so now if I want a new dictionary that is a sorted copy, sorted by key, of that dictionary, I can say my new dictionary, dsort, is a dictionary constructed from the sorted items from D. Okay, d.items is going to be tuples, two tuples specifically, key value pairs, and I can construct a dictionary from key value pairs, an iterable on key value pairs, and so poof, dsort does have the same contents as D, but sorted by key. Okay, so you can't directly sort a dictionary internally, but you can obtain a sorted copy of the dictionary, and from that just create a brand new dictionary. All right, well, now onward to part 2, more stuff that we missed. The stir data type, each stir object, contains a sequence of Unicode characters. And virtually all written human character sets can be represented in the Unicode character set. If you're not familiar with the Unicode, you can just Google for Unicode, and the Wikipedia page about Unicode is very thorough and very long and will tell you way more than you have time to learn. But given some character as an argument, the ord standard function returns the ordinal or numeric value in the Unicode character set for the character. So in other words, if I say ord of little a, the value I get back is 97. Now, that happens to be within the ASCII subset of Unicode. And little a does have an equivalent base 10 value of 97. If I ask for the character corresponding to some arbitrary number or so-called code point, the code points are the integer values that you can use, and those values range from 0 up to a bit more than 1 million. Because of the huge numbers of written human character sets with, different cases and all kinds of special characters and blah, blah, blah. So if I ask for the character corresponding to the code point 65, that turns out to be the capital A. All right, so ord and car are inverse of each other. And for ordinary keys on an American style keyboard, you get ASCII values. So the ord of capital A is 65. The ord of little a we've already seen, that's 97. The ord of the tab character in the ASCII character set turns out to be 9, whereas the ord of the new line character is 10. Okay? The ord of the character 0 is 48. So the decimal numbers corresponding to the characters 0 up through character 9, are from 48 through 57. So char of 57 is the character 9. Knowing about ord and char enables you to access characters that may not be available directly on your keyboard. Okay, here are some examples of the char function converting character value. Converting Unicode code points into the corresponding characters. But let me just jump ahead. Let's look at some symbols for money. That's always good. If you look up in the table for the euro symbol, that is hexadecimal 20AC. Okay, and that symbol should be available on any system that supports the Unicode character set, which Python does. Similarly, the British pound symbol has code point hexadecimal 20A4. And there are a couple, and there are very likely more, I just haven't discovered them. There are a couple of different symbols for the yen or yuan. FFE5 is the sort of, I don't know whether uppercase or bold is the correct term for that or what. And then there's also the 0xA5, which is an alternate version of that. All right, so you can find all of these symbols described in Unicode character tables. It's a little difficult reading through a million, but you can, you can search for what you want. All right. Well, next up, the hasAttr function is a standard function that checks a certain object to see whether it has a certain named attribute, and this is handy as opposed to just trying stuff out and having something crash. If I have a set of items and I say s.append a 12, well, that doesn't work because append doesn't apply to sets. For sets, we need to use add. If I had had the foresight to check, I could have used hasAttr to see whether S supports an append method or has an append attribute, and I get told no, it doesn't, but it does have an add attribute. Okay, so I can write code that checks objects for named attributes to determine which kinds of attributes and which kinds of methods are available for that particular object. IsInstance will test whether a certain object belongs to a certain class or category. This is more flexible than the straight type comparisons. For example, if I say type of 5, I get told that that's an int. And I can write code like if type of 5 equals int, then, display something. Yes. Type 5 equals int. Why didn't that print anything? Type 5 equal int. False. False. Wait. Oh, I probably need to use is. No. Well, this is a Oh, all right, silly me. All right. Um, I don't want to compare the type to a string. A type is never equal to a string, but the type of 5 is directly equal to the int data type. That's what I meant to do. Sorry about that. So that works fine. But the thing is, I might be interested in knowing whether if I say x gets something, I might be interested in knowing whether the type of x is int or the type of x is float if I want to do computations. Well, actually, Python supports a sort of a type hierarchy here, and I can ask whether some value is an instance of a number. All right, so if I say import numbers, then I can ask whether is instance 5 numbers.number, and because that's true, that implies I can do arithmetic with 5. Likewise, 2.7 numbers.number, and again, that's true. Okay, so is instance is more flexible than doing direct one-to-one comparisons of data types, but of course you'll have to read the documentation about that to familiarize yourself with the type hierarchy that is instance supports. For dealing with classes, there's a similar thing called is subclass, and this applies not only to the low-level data types, but it also applies to data types that you may have created yourself in your own modules. And I'm not going to do an actual example of this, but you may recall that way back when we defined an employee class, and from that we we used employee as a Sorry, C++ terminology keeps leaping into my head. We used employee as a subclass of manager. I keep wanting to say base class. And so I can ask now, is manager a subclass of employee? And I'll be told true. Yes, manager is derived from employee. String formatting. Well, I recommend that you acquaint yourself with the .format mechanism. You'll find that you can do about 99.9% of everything you want just using that subset of .format facilities that we discussed. There are other formatting mechanisms around, and you may encounter these in other people's code, so I just want to make you sort of briefly aware. The original formatting mechanism in Python uses the percent operator. You have a format string on the left, and then the percent operator, and then a tuple of values on the right, and the individual values within the tuple are then plugged in place of the format codes in the format string. Here's a trivial example. I'm going to use the format string, the value of, now %s, this is all pretty much directly stolen from the C language's printf function. %s means string. So the value of some string is %.6f. Now here, I'm saying that I want to print a floating point number. I'm not specifying the field width, so the number will be printed in as narrow a field as required. But I am saying that I do want there to be exactly 6 digits after the decimal point. All right, %.6f means show me a floating point number with 6 digits after the decimal point. Now, to feed values into the %s and the %.6f, I use an ampersand, a percent sign symbol, and provide a string and a number. Okay, now here on my slide, I imported math as m, and then I directly used m.pi. I'm just going to type in several digits, 3.1415926. Okay, so these are the values that I'm going to feed in for the string. The string is going to be pi, and the value is going to be 3.14159, and I guess that'll be rounded up to a 3. Yeah, 3.14159.3, since I asked for 6 digits after the decimal point. All right, so you might see the percent sign version of formatting, and that's, as I said, directly stolen from the C language's printf function. Here's a little more verbose thing. And let me copy and paste this so I don't have to manually type it. Whoops. My indentation got lost there. All right, so for val in range 4, in other words, 0, 1, 2, and 3, I'm going to display 5 8-character wide fields. All right, the first 8-character wide field is a float with 5 digits after the decimal point. The second 8-character wide field, again, is a float with 5 after the decimal. Then we have base 10 integers. 8-character wide field, 8-character wide field, and 8-character wide field. So I've got 5 8-character wide fields. Here's my percent sign. And then as my tuple, notice I can type my opening parenthesis for the tuple on this line, and that enables me to type subsequently on the following lines. I'm going to get the cube root, the square root, the individual value, the square, and the cube. So these first two are floats, and the following 3 are ints. There we go. All right, so cube root, square root, and then values, squares, and cubes for 0, 1, 2, and 3. Okay, we've already looked at the dot format function. I just wanted to show you one extra little trick about dot format. There's a lot more about dot format that I just am not interested in covering. But let's suppose that we create this list M. Okay, so this is the value 0. It's just the hexadecimal notation for the value 0, and that is an int. Then I have the string 1, the int 2, and the float 3.0. I am going to choose to display those, but not in that same order, not sub 0, sub 1, sub 2, sub 3. In this version of the dot format function, I'm using argument selectors to specify which argument should get plugged into which of these fields. So the third argument, which is going to be the 3.0 here, notice that I'm using my iterable iterable expansion, iterable... I've forgotten now what the term is. But anyway, so star M here is going to get replaced with these arguments. 0x0, comma, ONE, comma, 2, comma, 3. So in that order, I'm going to take the sub 3 one, which is 3.0, and I'm going to print that first in a field that's 5 characters wide with 1 digit after the decimal point. Then I'm going to print the sub-0 item, the sub-0 argument, as a 5-digit wide hexadecimal number. The second, the sub-2 item, which is just this number 2 here, is going to get displayed in decimal, 5 characters wide. And then finally, the string, the sub-1 argument, is going to get displayed there. Okay, so recall that numbers are right justified by default, whereas strings are left justified. So I've got 1, 2, 3, 4, 5 for my float, 1, 2, 3, 4, 5 for my hex. Now I'm a little puzzled why that didn't display as with a 0x. Oh, I know why. If I'd wanted to see a 0x, I would have had to stick a pound sign in front here. Let me try that. If I stick a pound sign in front of the 5, that means that I want to see the prefix. There we go. All right, so now I've got 5 for my float, 5 for my hex number, 5 for my decimal number, and 5 for my left justified string. All right, so numbers are right justified, strings are left justified by default. Okay, so not only can I alter the ordering in which the arguments are used in this way, but if I only have one argument, which would be the sub-0 argument, I can use that one argument multiple times by selecting argument 0 multiple times. Okay? Whoops. So let me run this one here. Okay, so I only have one argument. It's the sub-0 argument, and its value is 13. And I want to print that 8 characters wide as binary, and then 8 characters wide as hex, 8 characters wide as octal, and then 8 characters wide as decimal, base 10. I'm not going to get any prefixes here. Let me do this again, but throw in my pound signs to get the prefixes. There we go. So I've got the 0B for binary, 0X for hex, and 0O for octal. All right, so we've got the old original %sign version of formatted output, the stir.format function, and we have what are called F strings. Why are they called F strings? Well, they're called F strings because you put an F in front. All right, so here's my F string. And in an F string, I can simply access variables by name. So I've got a variable here called TWO that has a value 2. And I can access the variable. I can actually do a computation involving the value of the variable, etc. So I'll copy that. Whoops. Going to turn off my highlighting. And I need to have 2 defined first. All right, so I'm going to display the value of the variable 2, the value of the variable 2 to the 1/2 power, in other words, square root. and then the value of the variable 2 squared. Okay, so 2 square root of 2, 2 squared. This next one shows the horrificness of specifying the field width and the number of digits after the decimal point. So I don't know. They've kind of lost me with F strings here. So in the first curly braced reference to this variable 2, I'm just printing the value of that variable 2. But in this next one, I'm printing the square root of 2, but I want that, whoops, my apologies. I want that to be in a field that's 10 characters wide, and I want there to be 5 digits after the decimal point. So I have to use this ugly nested curly braces stuff going on. And then it doesn't even do what I asked for. And I'm really not clear why. I did get exactly 10 characters of output. But maybe the 5 includes the decimal point. Frankly, I haven't bothered to look into that because honestly, I don't care. But again, you may encounter F strings, and so that's what these things are about. All right, so that takes care of random Python stuff that a lot of which is just worth knowing for its own sake, and some of which you will perhaps encounter, and so you need to be prepared. All right, that is that.